Hello. Alright, I seem to be online. Good morning. We are talking about the development of the nervous system today. This is the last part of embryology, the entire nervous system, including the special senses which outgrew from it. So that we'll do in the next class. Today, let's see how the nervous system develops. So, if you do remember that there was long time ago a neural plate. So we can start with that there was a neural plate on top of the notochord cord, that is, it was dorsal to the notochord, and then a neural groove developed which went inside and folded and became a closed cylindrical structure called a neural tube. And from it, certain cells, certain regions had already budded out to the side, which got detached and became a bunch of cells called the neural crest. And the epidermis, the dorsal epidermis on either side of this developing new rectoderm, approximated itself after the folding from one side to the other, the two lateral sides. After this whole thing got buried under the surface, it attached back over the surface to continue and form the complete dorsum of the fetus, and therefore the skin covering the back of the nervous system tube. And here somewhere they will also be developing the sclerotome, dermatome and myotome, which will cover and protect this developing neural tube after this bunch of neural crest cells have migrated away and become something else. So this I think you have already done in general embryology till now. We will look at details of how each bit of it progresses, but this is how the entire fetus is developing in the 9 months of pregnancy. So at 3 weeks, you already have a pretty well developed cranial end of that same neural tube. And then, because the whole fetus longitudinally is undergoing a folding upon itself, including its cervical region where the pharyngeal arches are developing, in front of it, a great deal of folding has happened, and inside the developing nervous system, very rapid differentiation into different regions is happening. At the same time, the remaining part after the folding is closely related to this pharyngeal and cardiac regions, and the rest of it will develop more only after the 8 weeks, the first 2 months, where the lengthening will have to happen with the lengthening torso. The body itself is lengthening, and the lengthening of the CNS will also happen along with it. The cranial portions of it will then go and occupy the developing cranial vault, because at this point all the soft tissue covering the head end is expanding hugely. So compared to this, the amount of soft tissue available here is huge. That which will become the facial and cranial skeleton and the viscera of the upper end of the body. And that's where the most cranial part of this neural tube will remain and will grow maximum compared to the rest of the neural tube. So by 6 months, you have the maximum development and differentiation at the cranial end, and the remaining is going to, the caudal portions are going to remain somewhat less differentiated, still retaining the architecture, the geographies which were there in the fetal development of that original neural tube. So we can still to some extent make out which part is which. We just give them different names. We say we call them alar plate and basal plate, and we said motor horn and dorsal horn, sensory horn. So those names in the adult in neurology will change, but the structure, the orientation, the locations will remain more or less the same. So wherever these extreme foldings have happened, that structure of the neural tube itself will also adapt to that, and we will look at how that differentiation proceeds. So we'll look at mostly what is happening within the cranial cavity, because what happens within the spinal cord is not as much differentiated from the original neural tube as what happens within the cranial cavity. That's also common sense. The brain grows much more in volume as well as in sophistication, and its commitment to a specialized cell line becomes so extreme that no neurons can then ever be replaced after a certain degree of differentiation. It becomes very, very important in terms of the pathologies, the maladies, the sicknesses you can have with this tissue, which is so specialized in its future development. So, coming to the formation of this neural tube, which is called a process called neurulation. So here we had the plate, right? We had the disc where the fetus was, the neural plate developed on it. There was an oropharyngeal membrane and a cloacal membrane right in the beginning. There was a notochordal process, and a primitive knot had developed. So you already know and you remember this part. At this point, when you took a section, when you took a transverse section, then you saw that there was a notochordal area and a notochordal plate. Then there was intraembryonic mesoderm. Then there was this neural fold happening on top of it. So the neural groove happened here in the posterior, or at this point we call it dorsal midline. Around it, or on its side, was the amniotic cavity, whereas on the opposite side was the yolk sac. The intraembryonic mesoderm was just ventral to it, but it was also a flat plate, and the neural tissue, neurectoderm, was also a flat plate. Then when the folding of this plate happened upon itself, the plate-like structure became a tube. Then closure has to happen for a tube to happen. Then a fusion happens mostly in the middle regions, which is the future cervical region of the embryo, leaving an anterior opening which is called a neuropore. So when the somite formation is happening and closure is happening so that it closes into a tube, the anterior part of the neural fold is beginning to grow hugely. It is bulging out. There's so much of material formed that it is bulging out forward, and it's bilaterally symmetrical left and right sides, and a neural groove is visible and present between the two of them. And at the posterior side also, beyond the fusion, an opening is left or seen. So this place from where the opening can be identified is called the caudal neuropore, and where the ventral side can be identified is called the cranial neuropore. So if you take sections in the anterior side, you see that you have the notochord, and then you have the neural groove. The neural crest is differentiating at this time. It overhangs when this closure of the neural tube is going to happen, and this portion remains as a separate piece of tissue material, cells, apart from the neural tube itself. In the meantime, the size and importance and cellularity of the notochord has much diminished and become a much small tissue, and the sideways, the somite part, the mesoderm part, is differentiating rapidly into the three parts of the mesoderm which we have done before, in front of which some vascular tissue is already differentiating. See here on the ventral side, we are not yet seeing, but by the time you see here, that means differentiation at F is happening faster than it has happened at E, and that is happening faster than it has happened at D. So it is proceeding from F anteriorly. The differentiation speed is maximum at the first place where it started, and slowly catching up and cranial and caudal to that point. And the same differentiation will happen forward and backward. The same tissues will separate out. So the same names are given. The surface ectoderm closes over and outside the neural tube dorsally, completing the dorsal future skin and exterior surface of the fetus, which is on the side of the amniotic sac with the amniotic fluid. Then the body folding will happen later, but at this point we are only looking at the way the neural tube is folding and forming. So in neurulation, what has happened is that the closure has proceeded much more than the previous picture. So you have a neural groove, you have a rostral neuropore, and you have a caudal neuropore. The neural tube is in the middle, and the somites are developing on both sides. So if you look at it from the side, this is where the somites are developing. This bulging tissue is therefore under this surface is the neural tube, and if you trace it anteriorly, you see that the body wall is showing a hole where the rostral neuropore is closing, and similarly a caudal neuropore is closing. At this point, the cranial end is forming a forebrain prominence. Already there is heart tube fusing, folding, forming the heart chambers happening, and almost you can see that the body wall is beginning to differentiate into the future shape of the fetus. There's a yolk stalk and connecting stalk. When you see it, this is of course diagrammatic. If you see it as a cut section at this point, what we will see is that the amniotic cavity is folding around the tail and head folds and coming up to the buccopharyngeal membrane and the anal membrane. Inside of that, you have the neural tube, which is blue, which has a central canal or a central cavity, right, which is open to the outside through this caudal neuropore, and again to the outside through the rostral neuropore, outside of which is the dorsal body tissues, mesenchyme, spreading out around the embryo. So when you look at it on the outside, you see that the pharyngeal arches have begun to develop, and already from that forebrain prominence, an otic pit and a lens placode are differentiating, which means the beginning of the special senses has already started. This we will look at later in the next class, but remember that the differentiation is rapid and it's already happening at this stage of the embryo, where inside the foldings of the cranial end are happening. On the outside, visible to us if we were to do a scan, would be the development of the otic pit and the lens placode. So what we do is we stage it by the stage of pregnancy and by the size of the embryo, the actual measurement size of the embryo and the number of weeks of pregnancy. I'll come to that a little later. So you remember the points of the two neuropores and how they are happening, cranial and caudal, to the development of the somites, and how the neural tube is developing and bulging in between that, and how its cranial end is much more prominently and fastly and speedily differentiating into its different parts. On the outside, the ectoderm is cooperating with it. It actually gets induced by the internal neuroectodermal development. The external ectodermal development gets induced, where they connect with each other, forming the placodes, which will form the special senses. We will look at that later. So inside of this neural tube, which is anyway a hollow cylinder to begin with, the internal cylindrical cavity will develop into wider areas as the external tissue of neuroectoderm is becoming thicker and thicker, laying down many copies of itself and then differentiating. Inside, the space is also becoming wider and dilated and taking up certain shapes and certain positions. So the brain vesicles will be the precursors to the brain parts that we see later. So in the beginning, we will when the craniocaudal folding of the embryo is taking place, the heart and the gut and everything else is happening ventral to it. There you have the forebrain developing in the cranial end with an optic vesicle already beginning to show a full flexure or folding, which is called the midbrain flexure, after which, caudal to which, you have the midbrain developing. Then there is a whole bulge of tissue and a flexure in the opposite direction. This flexure is on the ventral side, this flexure is on the dorsal side, after which the portion we call the hindbrain, which continues with the development of the neuroectoderm. Here we start seeing that the output, the neural crest tissue, would have separated out and start forming on the side. On the side, this is not part of the tube. On the side, it will start forming the spinal ganglia. So the neural tube remains as a tube. the separated out original neural crest cells will come to lie ventrolateral to it and form spinal ganglia, outside of which are the somite differentiation happening. Always notochord stays in the central midline, ventral to the neural tube, and it is a very important inducting phenomenon to keep for the notochord to stay there for till a good part of the development finishes. Ventral to it, the vascular system is developing, and then the whole gut system. So this region is going to differentiate very rapidly. So if you look at it without all the remaining confusing things, this most cranial part we call the telencephalon. Telos means far away. The farthest is the telencephalon, after which you have the diencephalon. This optic vesicle will differentiate into an optic cup and further things we'll see next week. But after the diencephalon, what the bend which is available is called the mesencephalon, which will become the future midbrain. Then there will be a bigger bulge which is protruding dorsally, which we call the metencephalon, which gets a flexure from the dorsal side called the pontine flexure, and then the remaining whatever is left behind is called the myelencephalon, which will therefore be the, after the pons will be medulla oblongata. So we have the myelencephalon and its continuity into the primordial spinal cord, and on the sides of it, bilaterally symmetrical, you have the development of the spinal ganglia, which is developed from a separate tissue which was originally neural crest. These neural crest derivatives are very often asked in your exam, but also even otherwise you must know. So to begin with, we have a continuous neural crest which is condensing and separating out on either side of the fused, folded, completed cylindrical neural tube, and this can migrate out. They do. A whole bunch of cells will migrate out and penetrate into other arenas to give rise to different cell lines. For example, they will get into the dermis of the skin as melanocytes. So the melanocytes everywhere from top to toe are migrated neural crest cells. Like that, they will also come and lie closer to the spinal cord in sets. So they will contribute to and form the spinal ganglia, which is just outside of the dorsal or the sensory root of the forming spinal cord. The spinal cord is anyway forming from the main neural tube, and dorsolateral to it, a bunch of neural crest cells will set up this spinal ganglia, and the cell bodies will be here, and they will grow into the spinal cord, the proximal neural process, and the distal process will go out and become the sensory nerve. Similarly, they will go and form the sympathetic ganglia, right? For that matter, autonomic ganglia, wherever the migration has happened. So neural crest cell migrate and forms ganglia of the sympathetic trunk, which are also closely related to the vertebral column and the spinal cord inside it. So this ganglion of the sympathetic trunk will have these multipolar sympathetic ganglion cells, the neurons. The Schwann cells of the neurolemmal sheath are contributed by the neural crest cells. The ganglia of the sympathetic trunk, such as celiac, superior mesenteric, inferior mesenteric, that is of the digestive tract. Then the plexuses within the intestinal tract, which are parasympathetic mostly in nature, the Auerbach's plexus, the myenteric, and the Meissner's plexus, right, the submucosal plexus within the gut tube. That migration has also happened from neural crest. Then the renal ganglion, which will govern the urinary system, and the suprarenal gland medulla, which is in structure and in function, it is a bunch of cells which work like a autonomic ganglion. So the suprarenal medulla chromaffin cells are also migrated neural crest cells. It's a nice diagram, but probably in your books you get them as lists, whatever it is. Please read up and remember all the derivatives of the neural crest cells. So coming back to what is happening within the developing brain. So that neural tube which has closed and which is now differentiating and folding upon itself, its internal cavity is going to be forming the vesicles, which are primarily called the forebrain vesicle called the prosencephalon, the midbrain called the mesencephalon, and the hindbrain called the rhombencephalon. Rhomboid is that shape, the diamond, because that's the floor of the fourth ventricle. So rhombencephalon is that part of the primitive brain which contributed to the parts of the future brain which form the boundaries of the fourth ventricle. That's one way to remember it. But you remember forebrain, midbrain, hindbrain, that's easy. Remember prosencephalon, mesencephalon, and rhombencephalon. Now, from the forebrain, the most farthest development, like we said, telencephalon, will be contributing to the cerebral hemispheres, and its central cavity will be the lateral ventricle. Now, this one becomes bilateral because the tip, the extreme extent of the neural tube, which is now closed, the neuropores have closed. At that point, it will bud off into two and form two exactly symmetrical portions, one on either side, and its anterior end will then become the lamina terminalis of the third ventricle. So this part will bud out, and the connection will be left as the interventricular foramen. So the telencephalon is the most furthest part of the prosencephalon. The next one is called the diencephalon, which will form the thalamus, epithalamus, subthalamus, all of that, and the hypothalamus, and together their central cavity will be the third ventricle. Then after diencephalon, the mesencephalon remains least changed. So out of the entire CNS brain portion, the mesencephalon still retains the structure, the locations, and the internal architecture of the more primitive neural tube. It doesn't change much, it just becomes bigger, more material is laid down, but its central canal remains in the same place. Its nervous grey matter, white matter remain in the same place as originally. That part is called the mesencephalon. We know it as the midbrain, and its central canal is the aqueduct. The hindbrain happens after this next constriction, and that rhombencephalon is further differentiated into a metencephalon and myelencephalon. Metencephalon becomes pons and cerebral. And just remember, this part may be a little difficult to remember. Just remember, metencephalon is proximal and myelencephalon is distal or caudal. The we have said spinal medulla, right? And medulla oblongata. So the word medulla came with myelon. So the myelon contributes to wherever the word medulla is, right? So we have medulla oblongata and spinal medulla, both of them developing from this myelencephalon, and they form the boundaries of the lower part of the fourth ventricle, whereas the metencephalon, pons and cerebellum, form boundaries of the upper part of the fourth ventricle, right? So I think this is a good diagram for you to remember what it was called right in the beginning, what it differentiated into. At least these 5 names you should know, and then now what we call them once the differentiation is completed, and what are the central cavities called. So this is a nicer diagram, just showing you that from the diencephalon also more budding is going to happen, right? There's going to be formation of the optic vesicles away from it, and so on and so forth. So that will come and connect up to the diencephalon. We'll see that later. But the prosencephalon is differentiated into telen and dien. The mesencephalon, there's no further differentiation. The rhombencephalon differentiating into meten and myelin, and then the remaining part outside of the cranial cavity, we will call it the spinal cord. So inside, same thing but a different view. You have a forebrain, a midbrain, and a hindbrain. So just at 4 weeks, this has already happened. You have a deep flexure of the forebrain upon the hindbrain, with the midbrain bulging from that dorsal side. But it's not really bulging, it's actually retaining its primitive dimensions. This one will now bulge much more, and this one will bulge more beyond of this bend. So we'll see that the forebrain is differentiating into a telencephalon and diencephalon, and from its surface outpocketing called optic vesicle will happen from diencephalon. Then this flexure will bend further, and this is already, we are at, let's say, almost 5 weeks. Few days, 1 week later, there is further differentiation. This is the mesencephalon is remaining somewhat narrow, and on the dorsal surface a groove or a bend is going to happen, and that bit is going to be called a rhombencephalic isthmus because it is going to be a bend connecting that mesencephalon to the metencephalon, and that's called the isthmus. And then you have the metencephalon developing rapidly and the myelencephalon beyond it, and this bit will start thinning and stretching and forming the roof of the fourth ventricle. So inside of all these external developments, you have from the ependymal roof of the diencephalon, you have the stretching into the left and right side cerebral hemispheres. So this portion remains as diencephalon, and these portions grow in all directions, anterior, posterior, medial, lateral, and become the big structures, the big bulgy structures of the cerebral hemispheres, which means this part plus this part is equal to cerebrum, and this part is equal to diencephalon, and its central cavity remains as third ventricle. So since it's an extension of the cavity, the connection remains as a very narrow interventricular foramen, whereas the extension of the cavity, because of this growth, grows forward, backward, and then on the folding grows inferiorly also and sideways also. So the shape of the ventricle and the shape of the cerebral hemisphere will change rapidly and overgrow this central bit from which it grew out of. Therefore, diencephalon will remain very small and the telencephalon will become very huge and very dominant and occupy almost all the space available on the sides of the developing cranial vault. So the right cerebral hemisphere is developing on all sides of the third ventricle in the middle, which is the central cavity of this diencephalon. So prosencephalon becomes telen and dien, and telencephalon becomes cerebrum, that is the hemispheres including cortex, white matter, and including the basal nuclei. The deep nuclei are also coming from telencephalon. So they've just given it different colors here. The diencephalon, remember, is including of hypothalamus, epithalamus, also pituitary, and the retina, which grows out from this optic vesicle. So this lining material is going to contribute to the optic cup, and the actual visual apparatus is pocketing out from it. We'll see it next week. The mesencephalon continues and remains as the midbrain. The rhombencephalon, its proximal portion we said is pons and cerebellum, is the metencephalon, so pons and cerebellum, both together only from this bit, and whatever is left behind after that is the myelencephalon, which is the brainstem of the medulla oblongata. Whatever develops caudal to myelencephalon, there's no sharp differentiation or external marker. Only later, once the cranium bones are formed, is we use a foramen magnum as a differentiation. We saw in cranial roots and spinal roots of, let's say, accessory nerve, 11th nerve. You have a continuum of roots, and only from where the nerve finally comes out from the surface of the brain, we make a demarcation. Okay, this must be the cranial part and this must be the cervical part, and we use a foramen magnum as a differentiator because of that. But otherwise, there is no external marker or surface where we say that the medulla oblongata finishes and the spinal cord starts. We are differentiating it from the point of attachment of the roots on the surface. Alright, so in terms of development, these names must be known, the terminology must be known. Same, another diagram, probably easier, just to show you. The brown part was the diencephalon, which has become your thalamus. The yellow part was, what was the yellow part? Over here, it seems to be forming, okay, it's buried in between, so it must be the midbrain. No, the purple part is the cerebral aqueduct, so this is the mesencephalon. So the yellow part there, if it is still part of the cerebrum, is because it's going to, the basal ganglia are going to form this part of it. This yellow is now unexplained, but it's probably the buried part on top of the thalamus, where the coronal radiator is coming down and joining up the diencephalon. And the purple part is what we're calling the midbrain, which is used to be called the mesencephalon. Distal to that or caudal to that is the pons, which is here, which was part of the metencephalon. From there itself grew out a dorsal portion. See, in a coronal section you can't make out, but behind, from that metencephalon itself, a whole bulge developed, which is therefore the same color here, and is the cerebellum, right? Which both of which are becoming boundaries of the fourth ventricle upper part, and the lower part of fourth ventricle is bounded by the medulla called the myencephalon, which I think can't make out the different colors here, but this continuity is to show that the medulla and the cerebellum together are forming the boundary of the lower part of fourth ventricle, and the green bonds is forming the boundary of the upper part of the fourth ventricle. So that's how the differentiation has taken place. The flexures of the brain are very important. Because of these foldings, certain stretching and lateral development took place. So we already saw that there was a very deep first flexure, then there was a second flexure here. So from the cranial end, the telencephalon is developing. We can see one bulge here, but there will be one behind the board. So there is a left and a right bulge. You'll see only one of them. Caudal to it, you'll see a full bulge of diencephalon, which will be bilaterally symmetrical and a midline structure, and its lower part, that is its caudal part, will become the hypothalamic region, beyond which is this constriction and this deep flexure, and then you have this whole bit was the mesencephalon or the developing midbrain. Now here a lip-like development is going to begin, and that portion is called the rhombic lip. So there you will have, because of the deep pontine flexure developing on the dorsal side, this structure, which was like a straight cylinder, becomes like a deep U, and in that stretching, the roof of the lip, the roof tissue, becomes very thinned out and develops an aperture which gets open to the outside, and that very thin cut edge of the roof of the fourth ventricle, if you open it, you see that this is the floor of the fourth ventricle, and from this across on left and right sides, thinly stretched out, would have been the roof of the fourth ventricle with the apertures in it, which will allow the CSF to come out of the ventricular system. This deep U-shaped bend is called the pontine flexure, and from the surfaces you can already see the cranial nerves are coming out. Beyond that bend is the myencephalon, which is the medulla oblongata, and then there is a last bend. From here onwards, it is straight within the vertebral column. So this formation of the brain flexures is an important milestone for the future development of these telencephalon, mesencephalon, rhombencephalon portions. Okay, I just want this is to show you the dorsal surface of what we are seeing here. Here we are looking at it from the side view, right? If you were to look at it from here, if your eye were here and you were looking at it from the dorsal midline, from back midline, this is what you would see, that the mesencephalon is developing in the front. This whole thing is stretching sideways. The dark blue would have been a sheet, a complete sheet closing over that with a central aperture left behind. So this sheet is being closed, and you have a central aperture called the foramen of Magendie, through which that the thin roof is perforated by that aperture, and the inside ventricle will communicate with the outside subarachnoid space. But to begin with, it is a big space, and through it you are able to see the floor of the fourth ventricle, and you're seeing that this thin stretched out space is forming the boundary. On one side is the cerebellar plate, which is, some part of it is extraventricular and some part of it is intraventricular. The alar plate and the basal plate of the nervous tissue, the neurons, the grey matter developing on inside are seen. And if you look at it holistically a little later, you see that the cerebellum tissue, the midline tissue, is differentiating into the vermis and its portions, including the nodule and the flocculus, and its side tissues is going to bulge and grow much faster, just like the telencephalon, and become the cerebellar hemisphere portion, and it's going to overgrow and overlap in over and behind of the entire medulla oblongata also. But to begin with, we can make out that there is a roof plate of the fourth ventricle with this development of the median It should be called median, one singular midline aperture, and two lateral apertures, which are the foramina of Luschka. These apertures are the only thing which is left of this original open communication, because this roof plate grows over and closes it. So you have a closed backside of the rhombencephalon, with the whole backside of the medulla oblongata coming right up to where the cerebellum is going to overlap it. So the beginning of the cerebellum is like this, where you have a central vermilion portion and two hemispheric portions which are clearly seen and differentiated, and then the overgrowth happens to the adult dimensions. So in the third week, there are three brain vesicles, prosen, meson, and rhombencephalon. In the fifth week, you have the cranial cervical flexure and 8 hindbrain rhomomeres, followed by formation of the pontine flexure. So first cranial, then cervical, then pontine. Right? First there was a cranial flexure, the first slide which I showed you. Right? Then you have this one. Then you have the cervical flexion, and then the pontine flexion. So the last one is the one we are seeing here. This one is the last one that we see. So this flexure comes in last, and this part of development of hindbrain is happening a little later compared to the what is happening at the cranial end. This rhombic cliff and proliferation of the cells in the alar plates at the junction of roof and neural tube is happening anterior to the choroid plexus, which will be forming for the fourth ventricle. So the archicerebellum, we've done this with cerebellar class, develops by 8 weeks of age, that is the flocculonodular lobe. The anterior lobe develops by 15 weeks, and the vermis is before the hemispheres. The anterior part of the cerebellum is before the posterior part of the cerebellum. If you can remember all of this, it's good, but you remember the words archicerebellum and remember the development of the flexures. And this I already showed you. So you have a cervical flexure. Was it there in the first? This one, it was there, you could see it. So the cervical flexure is happening first, then you're having the mesencephalic flexure, and last you're having the pontine flexure. So cervical flexure is differentiating the future spinal cord from the entire CNS within the cranial cavity. The mesencephalic flexure is differentiating the prosencephalon from the mesencephalon, right? The pontine flexure is differentiating the metencephalon from the myelencephalon. And this isthmus rhombencephaly is not a full flexure as such. It is the actually unfolded narrow part which is remaining, because beyond it the metencephalon is going to grow a lot more. It's going to grow and become bigger, thicker than the mesencephalon. Mesencephalon we know is the midbrain. So that is the narrowest spot. So beyond that is the pons. Pons is going to get much more tissue and become fatter, isn't it? So that is the isthmus rhombencephaly is nothing but the ungrown part which is connecting the mesencephalon to the developing metencephalon. So at 7 weeks, this is the position. By 11 weeks, this bit has become a left and a right cerebral hemisphere. It's beginning to look more like the adult function, and 40 weeks, that's at term. Just before the baby is born, you have the final dimensions of the CNS. Because of this rapid growth and differentiation, this tissue is vulnerable to intra-amniotic or intra-uterine insult, particularly through the earliest stages. We saw by 8 to 16 weeks, almost all the differentiation is already happening. So neural tube closure or folding or amount of tissue defects can happen throughout this period and will reflect as mental retardation even if the child is born live. After 16 weeks, when the early developments are all over, some CNS defects can still persist because of location of the CNS within the outside protective housing that has to take place. The cranial vault has to develop, the cranial base has to develop. The remaining structures, the vertebral column has to develop. If there are mistakes in that or mismatches in the speed of development, you can still have CNS, but there will be a different kind of defect compared to the neural tube defect. So that differentiation is made when we are looking at its pathology. We'll study about it next year onwards. But just remember, see, the entire weeks are vulnerable. There is no part of development where the CNS is not vulnerable. The other systems, you can say maximum you have to be careful up to 8 weeks. After that, we are not very worried, right? Whereas for CNS, you're worried throughout. Anything can happen at any time. And up to 16 weeks, what is found would be classified as neural tube defects, and after that we call them as CNS defects. So there will be functional deficits and visible or detectable minor anomalies, whereas before that will be major congenital anomalies. This particularly up to 8 weeks for all other systems, but even up to 16 weeks for the CNS. So if there is failure of closure of neural tube, what will happen? If that development doesn't take properly, there is groove, folding, closure, then it could be a minimal lapse, in the sense most of it has happened and only little bit did not happen. Like, then we would call it a neural deficit. You will see a lesion on the back of the baby, the dorsal midline, where some opening has been left behind, and these are called the spina bifida lesions. If it contains more amount of tissue, if it's less, there will be a deficit, and there may be, that will be the only thing seen, but you will see some deformities in the bottom end of the baby, like a club foot. Whereas if there is a bulging of the neural tissue along with the cavity of the tube, then you would have a meningomyelocele with or without a hydrocephalus, which is a bulging of the wall of the liquid on the brain, because it's not able to drain out through the normal development of the draining tissues for the CSF. And on the surface you may see a skin, and what has happened is the vertebral bone has not fused. There's a spina bifida. Underneath of that, the spinal cord is exposed, its dorsal midline portion is exposed, and you may or may not have any surface projection noting it, except a small tuft of hair on the surface. I'll show you a photograph. So this is the minimum that happens, and then it's called a spina bifida occulta. But very often it can also be a full-fledged spina bifida with a meningocele or a meningomyelocele, and with a visible body wall defect also developing caudal to the lesion. If it is much more pronounced than that and happening at the cranial end, then it becomes a meroanencephaly, or what is simply called an anencephaly, where you have a defective closure of the rostral neural pore. So you have incomplete development of the brain and degeneration of it, because it will be exposed. The cranial vault will not develop, the calvaria will not form, and the facial development will also be impacted. The auricles, their position, their appearance, their development will also be seen to be different. So this can be detected even inside even in an ultrasound examination, and we look for it in the antenatal examination of a pregnant woman. So the anomalies I've mentioned are microcephaly, small size brain; macro, large size; hydrocephalus, that is water on the brain; non-closure of the neural tube; rachischisis and anencephaly; bulging into abnormal spaces; encephalocele, myelocele. Just get used to the terminology: meningocele and cerebellocele and Arnold Chiari. I've got photographs of all this, but I'm running late, so I'll just show you a few photographs and stop, and we'll continue in the next class. So this is an encephalocele. This is a rachischisis, the acrania. The cranium didn't develop at all. See, the face has developed, but the cranium has not, and the brain has been completely distorted. This syndrome, you can see there is polydactyly here. You'll come across these words, just introducing you to the terminology now. So a spina bifida occulta, where the spine is deformed but not visible to the outside. Here there is a non-closure of the bone and a bulging of the CSF space, the subarachnoid space, but the spinal cord is still in the protection of the body wall. So there is a meningocele. Here you have a meningomyelocele. The whole spinal cord has pushed out into the surface, so it will be palpable. You can feel it here under the skin as a soft tissue, and it will be visible there also. There will be stretching of the nerve roots because of it. Displaced spinal cord dorsally. Here the dorsum of the spinal cord didn't form at all. Only the dorsal horn is there. The ventral horn didn't form at all. Right, dorsal horn with dorsal roots are available. The ventral horn didn't form at all. So it's an open spinal cord, and that's called a myeloschisis. So spina bifida occult, only a little tuft of hair at the back, but that child has a vulnerability to damage of the spinal cord at that point. Spina bifida with meningomyelocele will be visible at birth itself. With a myeloschisis, you're actually seeing the surface of the spinal cord, and you're seeing that it is an unfused spinal cord. It's not a tube, but rather a splayed out region. This is seen at autopsy. So since time is up, I think I'll catch up, or let me see. Okay, I'll just rapidly finish this just to show you the development of the sulci and gyri on the surface. You know this is what it should look like. But this is how it proceeds from 14, 27, 30, 32 weeks. You can see the smooth surfaces becoming the corrugated surfaces because of the development of the sulci and gyri progressively in the cerebral hemispheres. Right? I won't go into the details except to tell you the names of the anomaly of formation. You have to listen carefully with almost bald, no development. Focal agyria. Here gyri are formed, but here in this region they have not. Only in some region you have non-formation. Rachischisis and polymicrogyria. Everywhere you have gyri, but they are few. Many, but small gyri. A holoprosencephaly could be of a alobar, semilobar or lobar type. Okay, I think I can jump this section. Formation of the, or we can stop here, and I will continue from here onwards, development of corpus callosum in the next class, because there are certain anomalies which we can make out in the antenatal scans. So in the next class we'll do this, and we will complete development of the special senses. I'll try to be a little faster. But remember the flexures, the names, the primitive names, and the fetal names and the adult names of the tissue as well as of the cavities, and what all anomalies can happen with that. So we'll close this for now. I'll catch up with you next week.